Acceleration. So our goals for this session are the following. We'll talk about acceleration, look at some equations we apply when the acceleration is constant. We'll look at free fall, which is a good example of motion with constant acceleration. And finally, we'll learn how to interpret graphs relating to an object experiencing acceleration. So what is acceleration? Well, it's a vector representing how fast and in what direction an object's velocity is changing. So in other words, acceleration is the time rate of change of velocity. Here's our equation. Average acceleration, a with a bar on top, is delta v over delta t. And in the limit that the time interval approaches 0, the average acceleration gives the instantaneous acceleration. If the acceleration is constant, then the instantaneous acceleration is equal to the average acceleration. Okay, so let's think about direction. Some people get confused by what acceleration positive or negative means. Okay, so here we'll define right to be the positive direction. And first we'll observe the motion when both velocity and acceleration are positive. In other words, they're both directed to the right. So the initial velocity was right, the acceleration is right. What you see on the motion diagrams, the dots get further and further apart as time goes by. What if both the acceleration and velocity are negative? Okay, so in the case of the bottom, the initial velocity was directed left, the acceleration is also directed left. They're both in the negative direction. It's really a mirror image of what we saw before. The dots in the motion diagram get further and further apart. Okay, so the basic idea is this. When the velocity and the acceleration are in the same direction as one another, the object speeds up. Okay. Let's look at the case when the velocity and acceleration are in opposite directions. Okay, so in this case, the initial velocity is to the right, but the acceleration is to the left. It's opposite to the initial velocity. And here we can see the dots in the motion diagram successfully get closer and closer together. So that's the case where the velocity is positive, the acceleration is negative. Okay, so let's do the case where the initial velocity is to the left, but the acceleration is to the right. Okay, so once again, we see the dots in the motion diagram getting closer and closer together as time goes by. Okay, so that's the situation of velocity is negative, but the acceleration is positive. Okay, so when the velocity and the acceleration are in opposite directions, that's both the two cases we saw on this page, the object slows down. So that's how to think about direction. You want to think about what direction the velocity is and compare that to the direction of the acceleration, and that'll tell you whether the object speeds up or slows down. Okay, so these are the constant acceleration equations we use to relate displacement, velocity, acceleration, and time. Note that everything except time is a vector component. It's a scalar with a sign. Okay, time is just a scalar. And you use appropriate plus or minus signs to indicate the direction of those vector quantities. Okay, so we'll measure time from t equals 0, and the acceleration is constant. A word about that last equation. That first part of it, xi plus v of t, average velocity times time, is true all the time. It's generally true. And it's just this second part which is only true in the constant acceleration case. Okay, so where do these equations come from? Well, the first one comes from the definition of acceleration. The last one comes from the definition of average velocity, and the other two come from combining the first and the fourth. For instance, if you take the v as vi plus at and replace the v in the last equation by vi plus at, you will get the second equation. And if you solve for time in the first equation and plug that expression for time into the last one, you will get the third equation. Okay, so that's where they come from. Okay, so let's make use of motion graphs. So we already looked at position and velocity and see how they're related. Well, velocity is related to position the same way acceleration is related to velocity. So the instantaneous acceleration is the slope at a particular instant on a velocity versus time graph, while the change in velocity is the area under the curve for a particular time interval on an acceleration versus time graph. Okay, so we'll look at that for free fall. Okay, so here we have an object will drop from rest from a height of 20 meters over the ground We'll approximate the acceleration due to gravity as 10 meters per second, 10 meters per second squared, directed down. In other words, the velocity changes by 10 meters per second every second. Okay, so here's our falling object. And you can see the motion diagram. The dots get spread farther and farther apart as time goes by. Lovely. And here's our graph of acceleration as a function of time that goes along with that. You see the acceleration is constant at minus 10 meters per second squared. Okay, great. So now we'll look at it again, but what we're going to do is we'll use the acceleration graph to find the change in velocity. The change in velocity is the area under the curve. Nice rectangle. The area is the height, 10 meters per second squared with a negative sign, times the width, 2 seconds. That's an area of minus 20 meters per second. What does that mean? That means the velocity changes by minus 20 meters per second. In this case, it started 0 meters per second, so at the end, it's going negative 20 meters per second. That means 20 meters per second down just before impact. Okay, what about the velocity versus time graph? So here's our same motion diagram, and then we'll draw the velocity versus time graph that goes along with that. And here's our constant slope graph of velocity versus time. Lovely. The velocity changes at a constant rate. The slope is constant. Okay, so now we're going to check that the slope of the velocity graph is the acceleration. So here we can use the whole graph because the slope is constant. So the slope is the rise over the run. It went down 20 meters per second while it went across 2 seconds. So we'll say the slope is minus 20 meters per second divided by the 2 seconds. That is indeed minus 10 meters per second squared, which corresponds to the acceleration. Okay, so that's what we can use graphs to tell us a lot about velocity, change in velocity, acceleration, and things like that. What about the position versus time graph? Okay, so let's see what we got there. Remember, the velocity is the slope of the position versus time graph, and that slope is steadily changing as time goes by. So we get, in fact, a nice parabola on the position versus time graph.